morning, everyone. My name is Alexi Lynch with Q1 Productions. It's my pleasure to welcome you today to this webinar hosted in partnership with IBA, and that will focus on internalizing a 1 to 2 MCI equivalent X-ray sterilization facility, a customer journey from product qualification to autonomous operations. It is the first webinar within a series on leveraging on E-beam and X-ray solutions to secure the near-term sterilization capacity, status, and testimonies. Do make sure to stay with us until the end of the webinar today, as we will tell you more about the next session within the series that will take place in October this year. About our speakers, we have Tim Thompson from Arthrex. He is currently the Senior Director of Operations and has been with the company for the last 11 years. He has overseen the design and construction of a 55,000 square foot sterilization facility located in Florida and has overseen design and the current construction of an in-house irradiation facility. This newest facility will have both E-beam and X-ray capabilities located at Arthrex's new manufacturing campus in Anderson, South Carolina. Prior to Arthrex, Tim's tenure included roles with Medtronic, W.L. Gore Medical, and Sterigenics. Joining Tim, we have Arnaud Pierrat, who is a product manager with IBA. He started working for IBA Industrial in 2015, working on commissioning and maintaining Rhodotron electron and X-ray accelerators all over the world. Using the technical knowledge and expertise from this field experience, he transitioned as a product manager at IBA Industrial to oversee the new technological developments and features of the Rhodotron. In this context, he contributed to the launch of IBA Industrial new portfolio of integrated solutions, Beyond Solutions. It's my pleasure to share their presentation with you today. Thank you.
First, I want to thank Tim for accepting to talk with me today about his experience with Arthrex during his collaboration with IBA. And the topic really is about how we build and design together IBA and Arthrex an X-ray irradiation facility, which is equivalent to 1 to 2 megacurie irradiation gamma center. So to give a little bit of context about how where we are today in the world of the medical device sterilization market, what we see is that the medical device market is growing and is expecting to continue growing at about 7% per year. And today, the different modalities that are available for the industry to make sure that those products are sterilized is mainly ethylene oxide, which is a toxic gas which kills the bacteria and every kind of contamination that you might have on your products. Gamma rays, which are made with cobalt-60, so a radioactive material. And then you have electron beam and X-rays, which are generated just from electricity, so no gas and no radioactive materials. So today, what we see is that ethylene oxide on one side is facing issues with, regulatory problems, issues with the environmental problems as well. And on the other hand, gamma is also facing some issues with its supply. And the main reason for that is that it's the production of gamma is actually very concentrated in a few countries. One of them, which is Russia, with the ongoing war with Ukraine, it's bringing quite a lot of questions about how to get your hands on gamma, because you need to replenish it every few years to make sure that you keep your capacity, irradiation capacity. So seeing this whole picture, what we expect for the next years is that gamma is going to stay there, ethylene oxide is also going to stay there, but to really capture this growth in the market of medical device that we see, we are going to need some electricity-based irradiation solutions, such as electron beam and X-ray. So we really expect that those 10 to 11% that we see there on the chart on the right is going to be more than that in the future. Of the two, so of electron beam and X-ray, X-ray is really the one which is closest to gamma irradiation today. So in this context, for medical device manufacturers, it's really important to be able to sterilize the sterilization capacity. And one of the way of doing that is to integrate in-house the sterilization process. So this brings a lot of advantages. And we are going to see together how IBA and Arthrex designed a solution to bring in-house the sterilization capacity to Arthrex. So this starts with the first idea. Then we need to know exactly to define what we're going to do with the solution, to evaluate what makes sense, what is the solution exactly that we need, to design it. Once we know what we want to do, we need still to design it, to engineer everything. We need to make sure that the financials make sense. And then once all of that is agreed upon, we need to start manufacturing the equipment, installing it, starting it, doing the commissioning. And then after this comes the customer care and basically all the life of the equipment. To go through this journey that we had together and that we are still having together, we will look at how it started with Arthrex, the challenges, the opportunities that they had a few years ago when we first started the discussions. We are going to take a look at the products that Arthrex is manufacturing. What did we know at the time? What did we still needed to know in order to make sure that what we were going to do with the products makes sense? Then we will go through the steps of evaluating the modality, so how to go from gamma to X-ray radiation. Then we are going to talk about designing the solution that is going to make sense for Arthrex, evaluating the business plan. And then what comes after is really the start of the project, how IBA makes sure to be available to make it a smooth process. And then the next steps about how we can take this even further to go beyond together and really improve the system over its lifetime. All right, so Tim, I'll let you the floor.
Thank you, Arnaud. Good morning, good afternoon. It's very nice to be here. I know we've been working on this project for the last 3+ years, and I think this is a great business model to show how effective it can be for an equipment supplier or a technology supplier and a customer needing to use that technology can partner together to make this process really work, because obviously IBA is the technology leader and real knowledge base that we've drawn upon to help us understand the feasibility of this project from a financial standpoint, from a throughput standpoint, and really, you know, having limited experience on our team with specifically with X-ray and E-beam, it makes it that much more beneficial to have a partner kind of walking along the path with us. So thanks for that. A little bit about us. We are a orthopedic device company. We are headquartered in Naples, Florida. Our corporate mission is to help surgeons treat their patients better. And we have pioneered the field of arthroscopy, and we have more than 1,000 new products introduced into the market every year. We service a wide variety of orthopedic fields, including the hand and wrist, foot and ankle, shoulder and elbow, along with arthroplasty for the knee and shoulders. So we're moving more and more into total joint replacement. So you can see a couple of pictures of some of our devices there that shows a little bit of the diversity of the product size, product density. So that's a couple of the things that we had to really work through with IBA, was understanding, you know, our current modality for sterilization, and then how do we move to X-ray and E-beam with those same product families, product densities, the whole 9 yards. So when we first started having discussions with IBA, we have in-house ETO processing that provides sterilization for about 60% of what we manufacture in the United States, both at our manufacturing campus in South Florida and a newer manufacturing campus that we've just started over the last 3 to 4 years in Anderson, South Carolina. So we continue to grow. We expect to see anywhere between 15 and 20% growth year over year for the next 5+ years. So we are growing exponentially, and it's a problem, but it's a great problem to have. So part of the reason that we really look at this solution is because of the innovative nature of it. And I know that's kind of a business cliche, and you hear that all the time about wanting to be innovative, but this really is an innovative answer to being able to vertically integrate our sterilization in-house. And that was really the main goal of this project. So we currently have about 40%. The other 40% that we manufacture in Florida and South Carolina is gamma radiated in a third-party supplier here in Central Florida. So that's kind of where we stood when we started to talk about the possibility of bringing a radiation processing in-house. So the issue with this model is obviously with the growth rate that we are undergoing, it really behooved us to look at, does it make sense to bring this process in-house? Obviously, there's a capital expenditure that's required. There's regulatory approvals. There's submission changes and everything that goes along with a new modality or a new location for sterilization. So all of that had to be weighed against cost and then time savings and freight savings. So in the end, we really wanted to partner with a supplier that could kind of help us answer the majority of those questions by using their templates for throughput, for energy requirements, for future growth. And IBA in the beginning, with kind of the interaction that we had with the project managers and sales, really were able to really pitch in a lot and give us the information that you've built over the years with other projects. And now is templates for the financial aspect of things or the throughput aspect of things, and looking at our products, density mixes, and you've done a lot of work with our throughput as well. So there's a lot of cogs that have fit together really well when trying to understand if this project made sense or not. So we traveled to Belgium back in 2020, which seems like 20 years ago, but it was relatively not that long ago. But we traveled to Louvain-la-Neuve and visited the headquarters there with IBA and looked at their assembly, and they were building accelerators there at the time, and the sales manager for IBA was kind enough to take us on a trip to Austria and to Italy. Austria, we were able to visit a current customer of yours there who has a Rhodotron installed, and we were able to see that process, and they were courteous enough to take us kind of through the maze and showed the Rhodotron to us, and it was a really impressive operation there in Austria, and so we were really impressed by that. And then we went to Parma, Italy, to tour the conveyor facility that you partner with, Acme, and saw they had a conveyor set up for an FAT for a customer, and we were again fortunate enough to be able to step in the warehouse and watch that process. And the conveyor, as we'll talk about later, the conveyor is as important a part of the project as the Rhodotron itself. It might not seem that way, but it turns out that's one of the things that we've learned over the last few years is that the conveyor and how that ties in with the energy delivered from the accelerator, and you'll talk a little bit later about how the gaps between boxes and things like that really are critical to throughput and downtime. And so it was a great visit, and I think that plus the history that IBA has with accelerators in the field, their expansive product manager and technical support folks, the projects they have ongoing, And for us, really, the ability to do both E-beam and X-ray with the same accelerator with two separate paths using the same conveyor setup was really kind of the seller at the end of the day, because we knew we wanted to have both capabilities. X-ray for that similarity to the energy that's provided by our current gamma supplier, and then E-beam for future growth, lower density products that we might be able to convert easily, even some chemistry things that we might be taking a look at, like polymer chemistry, cross-linking, and things like that that might improve our product performance down the road. So that was the big selling point.
All right, thanks, Tim. Now, to talk about the products that you have to, that you have to take care of and that you need to sterilize. There are a lot of them. They are quite specific. It's not your standard medical device that you see every day. I mean, maybe you do, but I definitely don't.
And another big challenge of this project due diligence was just understanding that we have large products that like may weigh half a pound here. Our largest shipper, 5x6 by 16, weighing half a pound, and then we have millimeter screws and plates that weigh just grams a piece. So the density families are spread out pretty significantly. So our engineering team, led by our engineering manager here, really had to do a lot of testing and due diligence in terms of, can the same energy delivered, with all 5 or 6 of our product density families provide that same level of sterility, provide the same level of packaging performance and product performance, right? So that was a big deal for us. So we have 10,000 different SKUs, and like I said before, we introduce about 1,000 a year. So it's a lot of administrative tasks keeping up with all those different families. But packaging constructs, we run the whole gambit from lids and trays to foil pouches to Tyvek pouches, just about everything that you can have in terms of a packaging construct, we pretty much run. So we do have 2 dose ranges, 25 to 35, which is pretty tight, with a tight DUR, and the dose uniformity ratio a little bit higher for our standard product lines, is at 25 to 45 kilogray. So we process on an annual average about 300,000 cubic feet of product. And we've irradiated those products here in South Florida for the last 20 years. So this is a big change for us. Our biocompatible, bioabsorbable materials are the critical ones in these processes. That's the tight 25 to 35 DUR, 25 to 35 kilograms dose range. And they're really temperature sensitive. So a lot of due diligence was done around processing our biomaterials, trying to ensure that we don't have a significant temperature increase during the processing time. So that was all part of our initial testing to prove viability for the project.
Right. So I guess the next step was, like you said, you had done a lot of due diligence to really make sure that the products would be compatible with irradiation in general. So I know that you've run some tests in Austria actually to validate the first assumptions. How did that go? What made you, was it convincing? What did you decide after that?
Well, again, thanks to our friends in Austria at Metascan, because they ran a lot of boxes for us, and with dosimeters all over the place with different placement strategies. And kudos to our partner in Strasbourg, France as well, Ariel and Felix, for also processing a lot of sample boxes for us on their small test center. So we really appreciate all the help that we've gotten from them. But in the end, it was, we wanted to verify that packaging considerations, product considerations, and dose uniformity was statistically the same or better than our gamma radiated products. And so we were able to do that through a myriad of tests. We were able to show that there was no significant statistical difference between the performance of all of our products and all of our packages at both min dose ranges and max dose ranges, and different box configurations, vertical, horizontal, product distribution inside the box was different. And so we literally ran hundreds and hundreds of boxes to show that this process was viable, and there was a real justification from a scientific standpoint that we should move forward with talking more about this process.
Yep, makes absolute sense. So already at this stage, a lot of work to validate everything. I know that there are a lot of initiatives going on to make this faster and simpler in the future, really to bring more information about the equivalency or not with between gamma and X-ray. So I think it's really, it's really important work that we need to do. And that also gives a lot of information about the products and how to process them in the best way. So to jump from there, I'm going to explain a little bit how at IBA we used all the information that Arthrex shared with us, really to define what was the best solution in the specific case of Arthrex. So what we asked for first is really the product characteristics, such as the box dimensions, the densities of the product. There we were actually lucky in a sense, because Arthrex uses mainly 4 types of standard boxes. So it makes things a little bit easier. But then at the same time, what they put in those boxes, like you've seen, there are a lot of different SKUs. So a lot of things to test. But so with this information and knowing what dose uniformity ratio we were aiming for, the minimum dose, in this case 25 kilograms, we got all of this information from Arthrex, and we were able from there to start thinking about, okay, what type of Rhodotron do I need? How much beam power is going to be necessary? Do I want to irradiate from the top laterally? And so the first thing is that for this study, even though we knew at this stage that Arthrex was really interested in having a duo Rhodotron to have both E-beam and X-ray modalities, the bulk of the work here was really focused at X-rays, because that's what Arthrex needs to bring back the sterilization in-house to replace gamma. And E-beam is an enabler for the future. So for this study, we really focused on X-ray. So, and the reason for X-ray is also because we, like Tim mentioned, we have very high density parts in the products, which would create some shadowing effect, and meaning that some parts of the products would not be completely sterile after irradiation. We have very tight DUR requirements, which are very difficult to reach with E-beam. So there it was the easy decision. It was the easy answer. It's okay, let's go with X-ray. Then we had to decide about whether we wanted to irradiate the boxes from the side or from the top. And here the answer was, again, pretty straightforward. The reason is that for a lot of Arthrex products, actually the cartons are not completely filled, which means that if you start to toss them around and to flip them to have double-sided irradiation from the top, it's going to be a mess, and it's going to be unpredictable in terms of dose in the product. And also, as you've seen, there are some products which are quite fragile. Again, you don't want them to move everywhere in a box. So this brought us to lateral irradiation, where we simply can flip the box without turning it and irradiate it from both sides. The beam power, we will talk a little bit after, but the beam power is actually the easy part of the equation. Because up to a certain point, the more beam power is simply equals to more throughput. So that's pretty easy, at least in X-ray. Then we started thinking about the type of conveyor and automation that we needed for this system. So do we want to use a box conveyor? Do we need some kind of trays, totes? Do we want to irradiate full pallets like it's done in X-ray with no problem most of the time? How fast should the boxes go under the beam? Do we need to have robots to palletize, depalletize automatically? Do we need to have automated storage? Those are all questions that we've asked ourselves during the design. And the first thing is that we know that Arthrex, when you compare to the big names in the sterilization industry, we are not looking at very high production volumes here. It's very specific, it's high value added products, and the volumes are not as big as some other players. At the same time, the batch sizes are pretty small. So you will have a few dozens of cartons of one type of product, then the next one will require different irradiation parameters. The dose uniformity ratio will be different. The DUR requirements will be different. And so again, this really doesn't fit with the idea of having a lot of products on full pallets and sending tens of pallets at a time in the system. At the same time, since we had already defined at this time that the system would not be like a very powerful one. So we are not talking about the TT1000 in this case with more than 500 kilowatts of beam power. It was simply not necessary, so it didn't make sense. And so that means that you don't need to have fast palletizing and depalletizing robots. You don't need to have huge areas to store all the products coming in and out of the facility. And the good thing is that the carton sizes, the standard Arthrex carton sizes that I've talked about, are very good for, I mean, the stability on a box conveyor is really good, because when you have boxes that are too tall, for example, they might fall over. When you have boxes that are too small, they might get stuck in the rollers of the conveyors and things like this. So that's all kinds of things that we have to take into account. In this case, we were kind of lucky because the box conveyor, the type of box conveyor that Arthrex visited in Ocme in Italy is actually a very good match. So once we have this, we start to have an idea of what we want to do. And then comes the time to really run Monte Carlo simulations, analytical estimates, and those mappings. So Arthrex had already done some of that previously, so we already had information, but we needed more. And then from there, we were able to estimate how much treatment time it would take to irradiate the yearly production of Arthrex, how much would be the maximum production volume, to take into account that it's going to grow in the future, and so we need to be ready for the future. So all of this is an iterative process, and we need to make decisions at each part of the process to really converge towards an optimal solution. So one of those questions, which had quite a lot of impact in the end, is that we had to decide how to position the box in front of the beam. So the first thing that we look at is the typical way we position box, especially in e-beam system, is that we place them short side leading. So that means that the shortest side of the box is leading the traveling direction of the box. The good thing with that is that since the short side of the box is going to be in the same direction as the beam won't need to penetrate a huge depth of product, which is going to lead to very good dose uniformity ratios. Now, if we look at the other alternative, which is long side leading, we see that the DUR gets a little bit worse. It's still actually pretty good for this specific box. So in this case, this wouldn't be an issue, but we know, like we've talked before, some parts of the inside the products are high density, and so the DUR for those types of products would actually be worse than this, which means that long side leading would not be compatible with all of our Arthrex products. So maybe you could ask, okay, let's do both, but then it's a matter of whether the operator is going to place all the time the products in the right orientation on the conveyor, and it brings some complexity that we didn't want to have. And so we decided to go with the short side leading. Now, there is a drawback of doing that, because if you just look at DUR, okay, DUR is better. But at the same time, if you have a smaller depth to go through, that means that more beam will actually end up outside of the box, behind the box, and hitting the wall and being lost and transformed as heat. So what we see here is the curve where actually the area under the curve is basically the energy that you capture in the product. And so if you have a larger distance of product in the path of the beam, you will capture more of this energy, which is going to lead in the end to better throughput. So knowing that, what we've thought about, and that was one of the big technical things that we had to decide with Arthrex, is what if we just use one carton in short side leading when the product requires it, when the DUR requirement is very tight, and for the other products which are not as strict in terms of DUR, we can just place two boxes next to, one behind the other, so that we can actually capture most of this energy for those products which are compatible, and so increase dramatically the throughput. So we will see that in the next slide. So if we look at the ratio of energy that's captured by the product, just because of the difference in depth of the product, we go from 47% to 72%. So that's a big difference. And in the case of this product, for example, the DUR stays very good. So for this theoretical product, it would be perfectly acceptable to have two boxes at the same time under the beam. And this would bring a tremendous increase in terms of throughput.
That was a big kind of a watershed moment when we got to the point where we said, yeah, we can run two side by side. That was a big step.
Yeah, absolutely. And so I was talking about how this is an iterative process. So one of the things that we have done. So if we go back to, okay, I need to treat just one box because this box needs a very tight DUR, and otherwise we won't reach the required DUR. If we do like what is typically do with this kind of conveyors when we work in E-beam, is that we know that we want at least two passes in front of the beam so that we can irradiate from both sides to get a better DUR. And normally what we do is we adjust the conveyor speed so that we can run the beam at full power, and we go faster or slower depending on the product. The problem with doing that is that we've thought that Arthrex actually has pretty small batches with not too many boxes. And in this case, we are in X-ray, not in E-beam. So the throughput rate, the rate at which the boxes can go under the beam, is actually much lower. So if you have a very low conveyor speed, and at the same time, you need to create some gaps in between the products that require a different recipe. The reason for this gap is that if you need to change the speed, you need some at least seconds to change the conveyor speed, maybe also the beam parameters. So this with a slow conveyor speed mean that actually you lose a lot of time waiting in between batches to clear that gap that you have to create, which is an inherent inefficiency in this process when we do it like this. Moreover, if you go very slow, you have a risk to have the temperature increase too much, and as we've seen, this is an issue for some of our Arthrex products. So what we did is that we decided to run what we call we deposit the dose in several steps. And so to do that, we decided to go with a fixed conveyor speed, which would be at least one order of magnitude above what we use when we did the simulations with variable speed. And then the way to decide how much dose the product will receive is we had to adjust the number of passes. So maybe a product will go 18 times under the beam. Some other products will have to go 26 times. And this can be really defined in the recipe. So doing this helps with increasing the max throughput because we basically eliminate one inefficiency. And at the same time, it brings the flexibility that we need for the system. Then the next iteration, like we said in the slide before, was to have two boxes under the beam at the same time whenever possible, which brings again a big gain in terms of maximum throughput. And then the last step that we've seen for this system is we know that I mean, we can decide to stack boxes on top of each other, and the idea with that is that we are able to basically use better the scan beam. The reason for that is that in X-ray, in order to keep a good DUR, you need to have quite a lot of overscan on the boxes. So we are talking about 20 centimeters on each side of the boxes. And so doing that, you actually get more out of the same beam. It has the impact, however, that we needed to increase the scan length from our standard 100 centimeters in X-ray to 140 centimeters. So that's something that we have developed specifically for this project. And the idea was really to make sure that we would be able to get a good DUR even with 2x2 stacks of box.
So it's an inherent, that's an inherent ability for us to grow, right? On day one, we will probably start with one box, 1 by 1, right? So then 2 by 1 by 2, and then a 2 by 2, right? So we've done nothing to change the energy of the system. We've not been required to increase power, but we've been able to go from 1 box process to 4 box process within the same design. So that was a really big, plus for us, and we owe it, mainly to you guys and understanding our product and being able to, do that iteration number 4 without changing any, of an additional expense for us. So that's a big plus.
Yeah, and so all of this, I mean, we've verified that in theory. So in theory is nice, but at some point you need to have facts and to prove that it's actually going to work and that we're not just, inventing stuff to make people happy. And so the way we did that is we put Arthrex in relation with IRL. So IRL is a research center in France, and they have a Rhodotron with X-ray capability at 7 MeV, so exactly what we are going to use for Arthrex. And so we were able to verify all these assumptions, so the 1 by 1, 2 by 1, 2 by 2 boxes, and make sure that the DUR that we calculated, the throughput that we calculated was actually in line with what we could measure in reality. So that was also a very important step to make sure that, yes, we are not running blindly. We understand the consequences of our decisions, and we can make an informed choice. All right, so now we know in theory what we need. So we have a pretty good idea of the type of Rhodotron, the beam power, what the conveyor needs to be able to do at what speed under the beam, how many passes, the DUR that we are going to have with the boxes. So we need to design it now. We know what we want to do, but it's still not not done yet. So there, Tim, you already talked a little bit about that, about the fact that you wanted an additional e-beam line, which was actually something that also drove some requirements more on the Rhodotron side, but it required some R&D from us. If you want to talk a little bit about that.
Yeah, when we started to take a look at the equipment choices that IBA provides, obviously we talked about X-ray and E-beam combined in the same situation. We had to partner with the conveyor supplier to make sure we could have both an E-beam speed, if you will, of the conveyor and an X-ray speed, which is significantly different, right? I mean, it's like a factor of 10, right? So we wanted to make sure that we had both of those, and IBA, and Acme both provided us with solutions. And so I think when we got to the understanding of, we had seen a TT300 already in Austria. We had seen one in France. We had known, that solution was going to be able to provide us with the energy required for the sterility of our product and the dose uniformity ratio that we needed, and that's what we really ended up, deciding on, kind of the mid-range size Rhodotron that would provide us what we need today and what we need 10 years from now, with the ability to add, boosters onto to the Rhodotron to increase that power supply over the years. So we don't have to buy another, accelerator. We add additional power as needed, and that's years out. But we did want to take a look at having the capacity to move some of our less dense products to E-beam eventually, to take advantage of that, that 10 times speed throughput, right? So evaluating those products with E-beam will be, another challenge that we'll take on. Kind of, this is Lego 1, and Lego 2 will add E-beam, and hopefully our polymer chemists will be excited about the opportunity to take a look at, can we improve some of the performance of our materials, whether it's plastics or metals, rubbers. I think they're excited about that opportunity as well. So that's how we kindly landed on the TT300.
Yep, and then for us, this this led us to think about how we want to integrate this TT300, because the one we were talking about in Austria is actually shooting from the top.
Yeah.
But here we know that we want to go from the side, so we had to do some thinking to decide what we could do. And so one of the questions was, do we want to have a separate underbeam area for E-beam and X-ray, having in mind that we don't want to have to pour more concrete than we need to. We don't want to have a weird product flow where some products get sent to the wrong underbeam and so on. And so we had some pretty weird designs at first that we considered, such as the one that we see here, where you would have an E-beam here, X-ray here, and then we don't know exactly how the conveyor here would have worked.
Yeah.
And so in the end, what we decided is, we know how to transport electrons at the exit of an accelerator, so let's use this knowledge. So what we did is, actually, we kept the X-ray line straight like we see here, and we designed a new magnet here that allows us to carry the electron beam from here to the electron horn here to make it parallel. So that means that instead of having this weird 2 underbeam conveyor, we just have 1 underbeam, a little bit longer than the standard, but basically otherwise it's really the same as what we've done many times in the past. And so this is the kind of things where we need to think, do we want to compromise on the building and the process flow, or can we bring some innovation to the accelerator part to solve this issue? So this also led to some thinking, which might seem not so important, but actually those kind of details matter, is that we know from our experience in X-ray that we need to be as close as possible to the product. Otherwise, the throughput goes down dramatically. And so that's really something that we had to keep in mind. But at the same time, since here we have 2 beams, two horns, we don't want either the electron horn to be too far from the product. Since those 2 horns don't have the same size, because there we needed to have 140 centimeter of scan, and here it's only 100 centimeters, we really need to take into account how to make sure that the product would still receive the dose like in a good way, even though the horns are different. So that's why we have this small dent here to make sure that the horn is close enough. We also had to make sure that the height of the conveyor was suited for both having enough overscan in X-ray, but at the same time also, being able to treat in E-beam. And so that's the kind of small details that it's easy to overlook them, but if you end up building a straight wall here, it's not fun having to dig into the concrete when it's done. So that's really the things that we need to take into account. It seems minor, but it's important. Then we had to think about how much ozone we are going to produce, how much, is the shielding that we designed able to stop the radiation? So that's the kind of things that we do there. We make calculation notes to show that the dose rate outside of the bunker is going to be below the limits accepted by the regulator. We also provide information about how much ozone production we are going to have when at full beam power, so that we can help designing the ozone extraction system and making sure that the system, when we start to make beam, is actually going to run correctly. On top of that,
just a quick note to jump in. And these calculations that IBA provided us were validated and rechecked by our own contract physicists, right? So we had a physicist who's certified in this, and he was able to do his own calculations and come up with basically the same numbers that IBA did, and was able to provide those to the local regulators, showing them that the building had been designed safely for both interior and exterior to the facility. So that was a big important step as well to get the building process started.
Yep. And then, of course, the building safety system is also very important to make sure that nobody can enter the system when any beam is on, to make sure that the safety of the operators is maintained and that there is no risk. So it's again, it's something that we do. It's quite standard, but making sure that we have the right doors, the right signals, the right probes, radiation probes to monitor the radiation in the vault area, but also outside. So those are all things that we have to take into account during the building safety design. Then the conveyor design. So that's also a big step. So as you may have understand from, by now, the guy Arthrex are really thorough. They want to make sure that everything is going to work well and to understand what they are doing. So that's excellent, because that forces us really to think about everything that could go wrong, about how the whole system is going to operate. And so regarding the conveyor design, we knew that we wanted to have 2x2 stacks of cartons under the beam. We knew that we didn't want to have any gap between the cartons. And again, that's because we don't want to be beaming air and doing nothing with it. And we knew that we had to manage many passes under the beam. So that was quite clear, but then we had a lot of questions that we needed to answer. So for example, how long is it going to take when I load the carton on the system until the treatment is finished and the carton goes out of the system, it's ready to be sent to the final customer? How many cartons do we need to have to make sure that there is no gap under the beam? Because if you don't feed it enough carton, obviously at some point you're going to have a gap. But how much is that? Is it 10 boxes, 50, 1,000? We needed to know. Then how many cartons can we fit in the system before we start to saturate it? Because there is only so much space on the conveyor, so we need to know that also, because basically we don't want products to be stuck under the beam, because that means that either you have to stop the beam or you continue irradiating a box that has already received too much dose, and this brings a lot of problems. So we need also to make sure that this wouldn't happen. We needed to make sure that there was enough accumulation zones to ensure a smooth product flow of the products on the conveyor, no jams, no gap where we don't want to have gap, and so on. We also had a request from Arthrex to understand a little bit better what a production day would look like. When will the operator have to load products on the conveyor? When will the operator have to unload them? So that's also the things that we needed to answer. And then also, how about, is my system going to be impacted if I choose one scheduling of production over the other one? So that's something that I will explain a little bit. But here is what we landed on. So it's actually very close to the standard conveyor, box conveyor that we have with Acme, where we can see a loading area, where actually we increase a little bit the size of the loading lane here to be able to provide some buffer so that the operator can load a lot of boxes and then go do something else while the conveyor automatically takes care of everything else. We have the treatment loop where the products will do 10, 20 loops, depending on the dose requirement. We have the underbeam area that we've already seen more in details. And we have the unloading area. In this case, one of the output of our study was that we needed multiple unloading lanes. The reason for that is that it allows to send a few batches of different products inside the treatment loop, and then you can wait for longer before the products go out, and the product A will come here, product B will come here, product C will come here. And so you don't have to be all the time standing next to the unloading area. You can leave it for some time, and then you can come and unload everything at once without mixing products, different products on pallets. So to do that, actually, what we've seen is that there was really one way to know if it was going to work, and it was to do a dynamic simulation of the conveyor. So we built a model to really replicate the alchemy conveyor, and basically we run it under different scenarios, different conditions, and we were able first to check that there is, the conveyor design, and it was not something that we doubted, but anyway, checking is always better than fixing afterwards. We were able to check that there is no jams occurring in the underbeam area, so we are never forced to stop the beam, and there is no issue with the product flows. One thing that we were also able to look at, it might be a bit scary when we see it like this, but once we read it, it's not so difficult. Here is basically a scenario that Arthrex sent to us, where we can see the production scheduling. And we see here that the idea was to work in 2 8-hour shifts, then shut down the system at night, and so on for the full week. What we see in blue is actually the indication of whether there is currently a product under the beam. So obviously we want to have products under the beam all the time, because otherwise that means that we are losing time. Then the red line is the percentage of time that the underbeam is occupied by a product. So again, we want it to be as close as possible to 1 at all time. The black line here is the number of boxes in the treatment loop. And so we see that it increases when we load the conveyor. Here, some products are treated and start to go out of the system, and they can be unloaded. Here we load again some new products because the production of the next day has arrived and is waiting for treatment. And then in green, we see the number of cartons that were successfully treated. So what we see in this scenario, where we have actually a set number of boxes arriving at the beginning of each day, is that we are not able to use the beam at 100% all of the time. During the first shift, the first 8-hour shift, it's pretty good. It's almost used at 100%, but then it drops. And the reason for that is that at this point, there are not enough cartons in the treatment loop to make sure that the underbeam conveyor is fed, which is a problem. Now, if we look at what happens is, if instead of having this limited amount of products at the beginning of day 1, we have the whole production of the whole week waiting for treatment on day 1, this brings quite a different picture, where here, since we have enough products to fully load the conveyor, we're able to use the beam 100% all of the time. And so we see that here that actually the treatment overall gets done more quickly than if we had the products arriving 1 by 1, let's say. And just here to the right, it's just the dosimeters going on in the simulation, even after there is no more products to treat. And so using all this information here, we were able to calculate how long it will take for a carton to be treated. So for example, if we look at the first one here, we see that after 1 shift, the first cartons start to go out of the system. We were also able to calculate and check how much cartons we need to keep the underbeam fed. I will take a bit more of a look into that in the next slide. We were able to see what a day of production would look like. For example, again, in this case, you see that here the operator is going to have to load products on the conveyor. here they are going to have to unload some products from the conveyor, and at the same time, if any products is available, load again more products. And so this also allowed us to have an idea of how much actually work it would take for the operators to load and unload this system, so that we could know, okay, that's one of the things that drove us to have those 3 unloading lines to basically to make the work of the operator so that the operator can work during half an hour unloading all the boxes instead of working 3 times 10 minutes, basically. Then what we did, based on all this information that we've had during the simulation, is check what would be the exact influence on the product flow of changing the underbeam speed. So we checked at 2 speeds, 1 meter per minute and 2 meters per minute. And based on that, we're able to calculate how long it takes for a box to go through the whole loop, and check that the number of boxes that we need to ensure that there is no gap here is actually lower than the maximum boxes that we can load in the conveyor, which is the case here. So I mean, that's a good check, because otherwise it's a huge problem. And we also did that for a different size of box. Basically, it's the same conclusion. We see that the number of cartons required to prevent the gaps is lower than the maximum number of cartons that we are able to load, so that's good. And at the same time, we see the influence of the underbeam speed, because we see that we need more cartons when the speed is higher than when the speed is lower. So this is something that's going to be important also to schedule the production flow and to make sure that there is always enough cartons in the system. Then we also took a look at exactly how much time a product will stay in the loop, and what are the implications of loading the conveyor as much as you can, or scheduling the production smartly so that you can really optimize the time that the product spent in the system. So here, everything here is the same. So 1 meter per minute, it's the same carton, it's the same number of passes under the beam. But here, what changes is the number of cartons in the loop. So in the first column here, we don't have enough cartons to fill the loop, because we've seen before that we needed 64. And so what this means is that you're going to, the cartons are going to spend more than 5 hours in the system. If we look at the second column, we still spend 5 hours, even though we have twice as many cartons in the system. And so in here, we have a perfect match between the speed of the underbeam and the number of cartons that we loaded. Then if we look and if we try to load the conveyor as much as possible, so the limit here is 167, what we actually see is that it's going to increase the total time spent in the loop, because the products, when they arrive here, will have to wait, because there will be a waiting line in this area. So you might think, okay, it's not a big deal, but at the same time, you have to think, okay, if I don't have enough products, obviously there are going to be some gaps under the beam. And so that's what we've seen. We're not going to use the beam as efficiently as possible. And so the throughput will be reduced. But then if you load it too much, well, you're going to reach 100% of beam utilization rate. And so the number of cartons per hour or per day that you are going to process is going to be basically the same, but the cartons are going to spend more time in the system. So that means that if you have an urgent production, you need to take that into account to know how long the carton will stay in the system, so that you know, okay, I'm loading this carton now. When is it going to go out of the system? And this depends on the number of cartons already in the system. So that's the kind of things that these dynamic simulations allow to understand. Okay, so now if we do the same thing, but with the other box, so a bit bigger, we see the same kind of results, where the minimum time is still the same because it's linked to the underbeam speed. But if you have a lot of boxes, again, it increases the time quite a lot. So, okay, that's the kind of things that we can help simulate and calculate. And what's interesting is that, I mean, when we've done the FAT at OCME, we will talk a little bit about that after. We were able to refine those numbers to check that our assumptions were good. And what we've seen is that we had been a little bit conservative on our assumptions, which was kind of the goal. But this was really to show that what we expected is the reflection of reality.
And that's a really important part of this, right? Is understanding, both throughput and efficiency. They don't necessarily go hand in hand. So this is a really big tool that IBA has provided for us, from a starting standpoint, to understand how to schedule effectively. Now, will we be able to provide the system exactly the same number of boxes and exactly the same number of boxes configuration-wise? Probably not. That would be, a blue sky situation. But we understand a lot better today about the efficiency differences based on these scheduling models.
So that was for the conveyor. Then if we need to take a look at the brain behind all of that, because it's also very important. So the process control system, the PCS that we have at IBA, communicating with the Rhodotron, with the conveyor, allows really to have a recipe for the products, to decide the beam power, to decide the conveyor speed, decide how many loops it will do inside the system. And so all of this is defined beforehand. Then you have the operator will load the box. The system will automatically do all of its things, so irradiating the product, making it recirculate the number of time that is needed. And in the end, what we have is a report that will show that, okay, the process parameters were in control during the whole irradiation of the product. We know exactly how much dose it received. We have dosimeters going in the system at frequent intervals so that we can make sure again that the dose matches what we expect it to be. And then this PCS, this process control system, in this case, needs to be able to track the boxes during the whole life on the conveyor, so with all the passes. It also needs to handle the fact that we have some boxes that will be treated in pairs and some boxes that will be treated alone. So we don't want to mix boxes that are treated alone and boxes that are treated in pairs. So that's really something that's quite important, to make sure that the pairs of boxes are defined from the start and they don't change during the whole process. We've discussed also about what happens if the beam stops and we need to restart under the beam. We have automated box labeling to make sure that we are able to track the boxes with barcode readers all along the conveyor path. We have an automated link to the dosimetry system so that when the dosimetry operator reads the dosimeter, it's automatically linked to the right batch of products. And we also have a link with the ERP system, again, to make the whole manufacturing flow easier. And then when we take all of that together, what we end up with is a solution. So with a conveyor in a building, so there Arthrex decided where to place the offices and how to make sure that the product flow from the in-feed with the trailers coming in to the outfeed, everything made sense for them. And so basically we end up with a solution that's able to be scaled up in the future. And it's roughly the equivalent of a 2 megacurie gamma sensor.
Yeah, this was a really nice, you kind of, not really the end, but a midpoint in the project where we got to the final construction design and got it approved, and we've already broken ground and started construction. We're probably about a third of the way into the construction process right now with pouring of the maze walls. I was just at the site yesterday and finished the last wall pour yesterday, and so the tilt walls are up and the office skeleton is up, so it's progressing really nicely.
Awesome. All right, and then for the next part, I will ask you, Tim, to talk a little bit about the business plan, how you made sure that all of the design work that we've done, all of this is nice and well, but if it doesn't make sense financially, it's not going to happen. So I leave you the hand for that.
Yeah, this is always the tricky part of the process, right? Doing your due diligence for the science, the sterility aspect of things. Those are straightforward, kind of yes or no. Can we do it or can we not do it? Right. So when we start talking about finances, you have to kind of temper some of that with expectations of what we're going to gain from this process, right? So bringing it in-house, we're not going to add any bottom line dollars to the company, but what we do provide as a service in this is time savings, freight savings, quality. We get to vertically integrate this process, right? So even to the point where we can bring surgeons in and have them tour the facility, and we hope that we take that burden of concern off a surgeon's plate, right? And we don't want them to worry about, is the product sterile or is this product, going to cause an infection or something like that. So there's a lot of little unknown, uncertain variables that you can't really put a price tag on, but that doesn't always answer the financial analyst's question. So when we started talking about capital expense, we had an expectation for a price, and this project was in line with our expectations for the size plant that we designed. Obviously, with the amount of concrete that's needed for this, adds a substantial chunk of money to the process, but obviously for employee safety and neighbor safety and everyone around the facility, that's an absolute necessity. So we put together a growth potential assessment with IBA's input. Obviously, we wanted to do all the experiments and due diligence to prove all this out, and that's really where we put together the comprehensive business case. We talked about throughput, we talked about the growth potential, we talked about the return on our original investment, which our analysts took our financial presentation and looked at it and said, yeah, this is in line with what we would expect for this type of investment, this type of process improvement savings. We're not adding dollars to the sales number at the end of the year, but they understand what that cost savings really pertains to. So they decided that a return was in line with our overall expectations from a corporate financial standpoint. So they really gave us the thumbs up at the end of the day. We considered building our own gamma facility, but this solution was much cheaper than that. Obviously, with the CapEx involved with buying radioactive material up front, is a substantial cost. But the nice thing about the E-beam and X-ray aspect of being electricity driven is obviously when the plant's not running, you can turn the system off and not have any costs associated with that. With radioactive material and other modalities, you always have that material half-life. So if you're running 100% efficiency, or if you're running 0% efficiency, you're always losing energy with that material, either out of the pool or in the pool. So that was a big consideration for us in terms of understanding kind of going forward, how do we save money and not have to replenish, a radioactive material on an annual basis. For us, in the end, when we started taking a look at the cost of what it would take with our current modality versus the cost for the throughput that we've done with all the calculations that you've seen Arnaud kind of run through, it's going to cost us about 50% less on day one than it currently costs us to have that material processed today. Now, this is not an indictment of our current supplier. We've had a long-running relationship with our gamma supplier for 20 years, and they have done an outstanding job for us. This is in relation to the growth rate that we're undergoing, and we don't feel like that system is going to be able to keep up with the amount of product that we're going to generate over the next 4 or 5 years. So we will continue to have a relationship with our gamma supplier and keep them fed with volume, where this facility, for the most part, is going to handle the growth that we're going to incur over the next 4 to 5 fiscal years for us. So we are going to optimize the process. We're going to meet with our boxing folks and packaging folks to talk about how to optimize, the products that we put in boxes, because as Arno, talked about with the conveyor design, we can't flip the boxes upside down, because in some of our boxes, they may be only 50% full. So obviously, if you flip that box upside down, everything falls to the bottom, and we end up, if we had a top-down situation, irradiating the top half empty part of the box twice. So that was a big decision for us to have to orient the box so we can flip it 180 degrees and then do it laterally and get both sides of the box in 2 different passes. So that was the overall business plan for us. We knew we were going to have to invest some capital. It's justified with our growth rates, and the return was acceptable to our finance folks. And we will whittle that down year by year as we optimize the process, as we understand a little bit more about scheduling the product more efficiently and things like that. So that's really where we ended up with our business plan. And the owner and founder, as his motto has always been, we try to have innovative solutions to challenges. And this, if not anything else, is extremely innovative in the way that we look at doing vertical integration of sterilization in-house.
All right, then after this, basically what was left to do is actually start the project and make this thing happen.
Yeah.
So you are in the middle now.
Yeah, we had a big project kickoff meeting at our Naples headquarters. We had everyone from IBA there. We had some accompanies folks with the conveyor system there. We had our architect and design firm that would put the plans together. Excuse me, for architecture standpoint and construction design, and all the Arthrex team there as well. So out of that, part of this schedule was what came out of it, right? So this was basically put together by our project manager, Fernand Willems, and he has done a great job with juggling kind of all the balls between the contractor and the architect and the subcontractors on the site. So this kind of gives you an overview of what the schedule looked like in a nutshell.
Yep. So what are the next steps now, Tim, for the project?
So next steps are really now to finish construction and get the building signed off from a construction standpoint. We'll bring the TT300 over later this year, rig that into place, finish up plugging the roof line after that gets put in place, and we'll kind of turn the ball back over to IBA and accompanies to do the installation of the conveyor and the Rhodotron, and we'll be there partnering with them. Our engineering and maintenance and facilities folks will be on hand to learn as much as they can as the process goes step by step through installation, and then firing it up and doing the installation qualifications. So it's going to be an exciting next 12 months.
Yeah, I think too. Excellent. And now just to go back a little bit back in time about the FAT that we've done with the conveyor at accompanies. If you want to share your experience with that, Tim.
This was really great. When we went to Bologna, Italy, I really didn't know what to expect in terms of, they said, oh, we're going to do the FAT. I was going, well, we sent a lot of boxes over, different sizes, different configuration, weights, the whole thing. And to walk into the Acme assembly warehouse in Emiliana Romagna, right in Bologna, it was fantastic. This thing is, when you when you see it on the drawing, it doesn't look that big, but when you see it laid out in a warehouse like this, it is massive. There's so many different features to this, from the control system that you can see on the left that tracks every individual box, to all of the placement sensors, to the labeling that puts on the QR code, all of the QR readers, the barcode readers, the dosimetry box, insert line. It was really, really a fascinating week to stay and watch all the different configurations of our boxes, the 1x1s, the 2x2s, and to see it operate and pick and choose, and to know the number of laps that each box had to go, and just all the different mechanical aspects of the conveyor. There's so many different roller types. There's the underbeam kind of chain conveyor, and there's rollers, and there's multi-dimensional sections which can make the boxes go one direction or the other. And it's really it's like when you're like a kid with the old train tracks or the old remote control cars. To see this thing work is really, really amazing. And you go, well, now I know why it's such an important part of the process, because it dictates the speed under beam, like you were saying, and it dictates how fastly the boxes can catch up and fill the gaps. And it was really a nice week to be able to go there. So thank you to all of our friends in Bologna and Parma who came down as well to help us with that.
Yeah, I agree. It's something when you see it run for the first time, it makes a lot more sense. All of a sudden, it makes things real.
It really becomes a reality when you see your product circling this monstrosity of a conveyor. It's really, really cool.
It's very visual also, because when you turn on the beam, it's exciting, but you can't go and see for yourself. So
right. It was really neat. One of our engineers actually had the funny idea. He taped his phone to the front of a box and basically tracked it around the entire path of the conveyor and made a little movie at the end. And we showed that to upper management here, and they really got a kick out of that. So it was a really good week.
Yeah, I agree. It was really nice. All right, then if we look at the next steps that we see from IBA's perspective, so obviously there is the commissioning of the equipment, but then one thing that we really want to emphasize is that we need to work together to make sure that you are going to be able to ramp up as fast as possible the production, so to help you with OQing the system and then running PQ on your products. Basically what we've done also for product scheduling, what we've done in silico, we need to help you make that happen in real life. So that's something that we are going to be present on site to make sure that it runs as best as possible and as quickly as possible.
And I know this is kind of an innocuous screen, but at the end of the day, this is as important a factor than any of the others that we've kind of gone through, because like everything we've done up to this point, for the most part, has been theoretical, right? We've talked about dose, we talked about throughput, we've talked about, the Monte Carlo simulations and dosimetry, and it's all been kind of back of the paper, physics that we've kind of worked out. But this, now saying we have a partner who's going to come and be on site, help us get up to speed with the equipment, be there to help qualify it and help, train and teach and be a partner. That's a big deal. And that was a big deal when we started talking about, the selection for the vendor on this project. This is an important slide, right? It's not one to be overlooked very, there's not a lot of information. It's not cool to look at, but in the end, this is the meat of a real partnership between Arthrex and IBA, and this is an important aspect.
Yeah, absolutely. And talking about training, it's also something where I'm doing a bit of promotion for this new setup that we have in IBA in Belgium. So we've actually brought a Rhodotron in Louvain-la-Neuve in Belgium to be able to train first our customers, but also our field engineers now go to the center really to get the basics of how to maintain and to fix any types of things that could come up with the accelerator, but also the PCS, so the Beagle PCS, know how to do basic dosimetry and things like this. And so far we've seen a lot of success with that, and this really allows to bring the team of the customer that will be on site to the level before the Rhodotron is even commissioned. So that's really something also that helps to ensure a smooth start of the system. So
we'll absolutely be taking advantages of this as well, because we have facilities technicians and engineers and people on site that we will want to go through this process as well. Now, we've had some folks train with Ariel on the dosimetry, and they've been great partners as well. Mm-hmm. We want to make sure that we continue to train all of our folks to be able to understand this process and be able to learn as much as we can before we start the system up next year.
Yep. And then for the last step, which is actually going to be the longest one, about maintaining the system over the whole lifetime. So today, where we are at IBA is that we're moving from a more European-centric customer base to really more worldwide, with a lot of activity in the US and in China specifically. And so to do that, to make sure that we are able to provide the right level of service and support to our customers all over the world, especially in the US, we've already hired a new, it's not brand new team, they are quite experienced already, but we have already 6 field service engineers just in the US team. We are also increasing our presence with the sales team, with product management, really to make sure that we are as close as possible to our customers in the US. And we plan to double that team actually in the coming years. So it's really a strategic goal for IBA to be present in the US, to be able to accompany our customers and to make sure that they are running as smoothly as possible, have access to all the spare parts that they need to have, and so on. And we are also building a network of third-party suppliers to be able to provide specific regional conveyors in several parts of the world. So really depending on the requirements of specific regions. So that's something that we are doing quite intensively right now, and it's really fruitful. It's really made things easier for our customers abroad. So that's a really, really important point for us today. And then if we look at what we can expect for the next steps in terms of technology, at IBA we have a few. We're also very innovation driven, always looking to try to make things better and to make things work in the best way as possible. And so today we have started a digitalization program really to enable predictive maintenance, smart maintenance, AI on our systems, and also a feature that's quite nice and that's very new is the variable scan in X-ray, which actually makes it possible to reach even better DURs than what we have with the standard X-ray scan today. So quite a lot of information, I think. So thank you so much, Tim, for speaking with me today. It's really a pleasure, and it's been a pleasure also working during the whole design phase. And I'm sure I will meet you on site once the system is installed. So
yeah, thank you, Arno. It's been a real great partnership. You've been fantastic, and all the team. You know, Gino back even when we first started the process, and Jeremy, Dominique, everyone on the IBA team has been really fantastic to work with, and we really appreciate the partnership. It's going to push this project to be a real success for us.
Thank you so much, everyone, for your kind attention. And thank you, of course, to our speakers once more, Tim Thompson from Arthrex and Arnaud Pierrard from IBA. As announced in the introduction, this presentation was the first within a series of webinars on leveraging on E-beam and X-ray solutions to secure the near-term sterilization capacity, status, and testimonies. The next session will take place October 5th and is going to focus on Monte Carlo simulations in radiation processing. It will be presented by Samuel Doré from Sartorius, Antoine Guillardi from TRAD, and Damien Priels from IBA. We do hope to see you tuned in for that session once more on October 5th. I would like to thank IBA for partnering with Q1 Productions for today's webinar and those to come in the fall. And once more, thank you all for logging in today and for your attention. You have a very good rest of your day. Take care.